Hello again. Many of our customers use our code software to develop and optimize coatings for architectural glass, and I thought it would be a good idea to have a basic tutorial which explains the idea behind those coatings. Let's start with a comparison of some office buildings. Here you see a historic office building built some 100 years ago, and on the left side and on the right side we have a more modern version of this kind of building, which has been built maybe 10 or 20 years ago. So big difference is, of course, the amount of stone on the left side is much higher than on the right side, and the size of the windows is also very different. On the right side we have basically a pure glass facade, whereas on the left side in the old building the amount of glass is very small. There are two reasons for this change in the way we build large buildings, office buildings. We can use glass now because of the introduction of a large-scale production of float glass. So to produce large amounts of thin, very smooth and flat glass has been improved a lot. As a second reason for the replacement of walls by windows is that we can now improve the glass properties by large area coatings. And this tutorial is about the function of those coatings and how you produce them. I will give you an overview on the important properties of glass and how they can be improved by a thin film system. Then I will discuss basically low E coatings, the simplest version of glass coatings, and then we go to some enhancement when I talk about solar control coatings. And at the end of the talk I will give an overview on the production and especially on the optical part that is used for production control. When you want to replace a solid wall by a window, by a transparent glass window, you have to take into account the thermal insulation of the building. Actually, what really counts is the so-called U value, which measures the heat loss per area of the wall and per temperature difference between the outside and inside temperature. And here are some typical numbers. A very simple thin brick stone wall has a U value of 2.2 watts per square meter and Kelvin temperature difference. If you use a more modern isolated version with maybe some foam insulation in between, you can reach values of 0.5 watts. And obviously the U value tells you how much money you have to invest in the heating inside the building, or in cooling outside the cooling inside the building if you are in an area which is much hotter outside than inside buildings. A single glass pane without any extras will have a U value of 6 watts per square meter and Kelvin. So that means that's more than 10 times larger than the insulated brick stone wall here. So the window would be a nice heat loss, and it would be very efficient to make this window very small so that you just can take a look outside but nothing more. That's how it was some 100 years ago. Then in the last century there was the invention of double glazing, in the sense that you take two panes of glass and you fill in a gas in between, and that reduces the heat loss by more than a factor of 2. This value, the U values are then 2.7 ideally, and but that's still much more than the volts that we are going to replace. So we have to do better. How can we further decrease the U value? So in order to answer that question, we have to take a look at the typical mechanisms of heat loss, and this is done on this page here. Here we have a wall on the right side, the frame of the window, and then here we have a double pane glazing, outside pane, inside pane, and some gas in between. Obviously, you have heat conduction through the frames here, which you cannot really avoid. There has to be a frame holding the glass, but of course you can build it in a fancy way to reduce that. That's not the topic of this talk. I will mainly focus on this main area of the glass. And here we have basically two mechanisms. First of all, the gas atoms, they hit the inside pane, they warm up there a little bit, take the energy of the warmer pane inside, assuming that it's inside warmer than outside. And then they carry this energy to the outside pane, and when they hit the outside pane, they deposit a small part of their energy there. So there is a net transport from through those gas atoms from the inside to the outside by convection. So you can reduce this amount of heat loss by using heavy atoms. If you do the math and the physics, you will find that the higher the mass of the atoms, then the lower this energy loss will be. So instead of air, usually people use argon atoms. Xenon would be even, or krypton would be even be nicer, but these gases are very expensive, and argon seems to be the best compromise at the moment to reduce this heat loss. Well, of course, this has nothing to do with coatings on glass, but the next mechanism, which is called radiation exchange between the paints, that can be influenced by coatings, and actually it can be almost diminished to zero by the proper coating of glass. So let's take a closer look at this effect. In order to do that, we need to take a closer inspection of the optical constants of glass. You can see a tutorial about optical constants in a separate video. Here I will just show you the refractive index of glass, in blue the real part, and in red the imaginary part. Basically, the real part here describes the speed of light inside glass, and the red curve here shows the amount of absorption. Here in the infrared region, at about 10,000 nanometers wavelengths or 10 microns wavelengths, we have very strong absorption. This is caused by vibrational modes. Basically, the light sets atoms in motion. Silicon atoms vibrate against oxygen atoms, and you do this by applying the electric fields of the light wave, setting the atoms in motion, and the atoms are have some damping to their environment, some connection to their environment. So in the end, the whole glass vibrates a little bit, and this means we convert infrared light to heat. Here we see on a logarithmic scale the intensity absorption coefficient of glass. Basically, these values are computed from the values that you see here. Here where K is almost zero, we have small absorption, especially in the blue and the green of the visible. The absorption of glass is really very, very small. But then if we go to larger and larger wavelengths, you can see an increase of the absorption, and here where we have the strong vibrational modes, the absorption coefficient is very high. This leads to the following optical properties of glass. In blue you see the transmission through a typical glass pane like 4 millimeter float glass, and in red you see the reflection. The reflection in the visible is about 8%, 4% generated by each interface. You have about 90% transmission, and the transmission then shows here the absorption processes in the near infrared, and finally, when the wavelength is long enough, the absorption coefficient is big enough, the transmission finally gets zero for mid-infrared radiation. So glass is absolutely intransparent for infrared radiation. There it shows some features in the reflectance curve generated by the vibrational modes, and this has a reflection of 10 to 15% on the average. The largest value is 30% only, so not very high. But in the ultraviolet, the transmission is also zero. That protects us from UV damage of our skin if we are inside buildings which have glass facades. But I will now concentrate on the infrared part of the spectrum. Let's take a look what it means to have reflection only a few percent and to have a zero transmission. That actually means the absorption is very high. It's typically 85% roughly, and there's a fundamental relation in physics. Whenever something absorbs, it can also emit radiation using the same mechanisms that you can use for absorption can also be used for emission of light. So when a material like glass in our case is a good absorber in the infrared, it is also a nice emitter. Basically, it's a radiation source and a very efficient, almost a black body radiation source in the mid-infrared. So if it has a certain temperature, let's say like room temperature, 300 Kelvin roughly, then a black body here would have this emission, the spectral distribution of the emitted intensity. And in this whole region, glass has an emissivity of above 80%. On the average, maybe 90%. So that means glass is almost a perfect black body radiator and absorber. So if you have this situation that you have an outside window pane which is cold and an inside pane which is warm, you have a net flow of energy. The inside is emitting to the outside absorbs everything, heats up a little bit, and emits back to the other side, but a little bit less. So there is a net flow due to radiation exchange. And you can see here the black body radiation emission of different temperatures. And even if there is a small temperature difference, this will generate a net flow of energy, which makes a large part of the heat loss of the U value of the window glazing. Okay, let's that was the wrong button, sorry. Let's think about reducing the absorption. Some people had the bright idea, if you want to reduce absorption, it would be the easiest way to do that maybe would be to deposit a thin film of a metal. That would increase the reflectivity or the reflectance, and if the reflectance is bigger, the absorption will be smaller. In our case, that means also the emission will be smaller. And in fact, the best material to do this is silver, and because only a few nanometers of silver, here I show you the curve for one nanometer silver on glass, ideally would reduce the emissivity already by a factor of 2. So this is the new emissivity, 1 minus R minus T, the absorption or the emissivity. And if you increase the silver thickness to 5 nanometers, you only have basically 10% emissivity anymore. If you go to 10 nanometers, you reduce it to about 5%. So silver is a very efficient layer to reduce the emissivity of the glass. Obviously, once you are very close to zero with the emissivity anyway, it's difficult to get better. So you need more and more silver to approach zero more and more close, and obviously you can never approach zero even with a very thick silver layer. So the best compromise should be somewhere in between. Let's take a look at the U value when you have the system float glass, argon, silver coated glass on the inside, and here I show you the U value for various silver thickness values. Starting at 0, we start here at 2.7. That was the U value of the uncoated double glazing, the historic version, and you can see that with 10 nanometers silver, we can reduce the U value by more than a factor of 2. So we go to a U value of 1.2, and with thicker silver, we can even get 1.1. There are some small details concerning the silver quality, which I will discuss later on. So, problem solved. Unfortunately, not completely. If we take a look at the reflectance and transmission curves once more, and now at the visible and the near infrared, and we introduce our silver layer, let's say 10 nanometers, you can see that the reflectance here in the infrared goes up. That's what we wanted. We wanted to reduce the absorption by increasing the reflection. But unfortunately also the nice transmission of the glass went down significantly, especially here in the red. It's only 1/2 of the value it used to be. It used to have. The reflectivity is also very different from what it was before. It's not 8% for almost all the colors, but it's now high for red radiation, for red light, and it's low for blue light. So a building equipped with this glass would look red, and if you look from inside to the outside, everything would look bluish because the blue transmission is much higher than the red transmission. Sometimes this is wanted. That's nice to have a nice blue world. But in most cases, the architects would tell you, no, we don't want red buildings everywhere. And we want to have a neutral color, if possible, especially for residential buildings where you spend a long time of your life. It would be very maybe annoying to see everything in blue if you look outside. So we have to repair this. And actually, it was shown in the last century, in the 70s and 80s, that we can repair this by 2 additional layers. And I will show that on the next page. Let's start with the 10 nanometer silver that we have discussed right now. And now we can take a look at another coating where we have between the silver layer and the glass a so-called bottom oxide and another oxide, a transparent oxide on top, which I call the top oxide. Typically for the bottom oxide, you would use titanium dioxide, which is a transparent material with a very high refractive index of roughly 2.4. For the top oxide, you don't need such a high refractive index. Value of 2 on the average and the visible seems to be sufficient. So you can use something like tin oxide as top oxide for this kind of coating. So let's introduce these coatings, starting with the bottom oxide. If we increase the thickness from starting at 0, we can watch the spectra. You can watch how the transmission here moves, the transmission peak moves into the visible, and the reflection dip also moves into the middle of the visible. So when we reach a thickness of 20 nanometers, in this case for titanium dioxide, the transmission peak is not so bluish anymore. It's more a greenish appearance now. We can do a little bit better if we increase the top oxide thickness, if we introduce that. So if we deposit more and more tin oxide on top, you can see that the transmission here rises and the reflection goes down. Let's see how far we can go. Actually, now I have already reached the transmission in the green, at least, of the uncoated glass. And if we increase it to about 50 nanometers or 55, something like this, we have a very broad minimum here in the visible. So the reflectance of this coated glass is even lower as before. Basically, the 3-layer system here on this glass side acts as an anti-reflection coating. So we are taking away the 4% reflection of the former pure glass interface, and we only get the 4% of the backside here. That's what we see here. The transmission is 90%, at least for the center part of the visible. We cannot really get the glass properties for red and blue light, so this will look a little bit greenish, but anyway, it's much better than the pure silver coated glass that we have seen before. Actually, we can now take a look at a building that would be equipped with such a coating. So this is a dual pane coating here on this window, and so this would be more or less a neutral appearance. This would have a more or less neutral color appearance equipped with this so-called low emission or low E coating. Actually, you have seen in the beginning already that we had reflection colors. So we could start by reducing the thicknesses again. We could start with red. If you want a red building, we can still do that. So if you tune the thickness, you can make a facade look like this. In many cases, architects prefer bluish, let's say bank buildings or buildings of insurance companies, something like that. If you want to have a bluish building, we have to go to larger oxide thickness values. So let's see how blue we can make it. Something like this should look bluish because the reflectance here is much higher in the blue compared to the red. And I hope this looks a little bit bluish. Not really nice as far as I can see on my screen, but anyway, different from the red that we had before. Here we also see an effect, of course, that I will discuss in a different tutorial, in a separate tutorial later on. The color of the glass depends on the viewing angle, and the viewing angle here is very different. Here we have maybe a an angle of incidence of 20 degrees, and maybe here we have 70 degrees. So we see the glass at very different angles if we are standing in front of a large building. And this will be one challenge of coating design, to make the color the same for different viewing angles. So if you want to avoid that the color here in this corner looks different from that corner, you have to do some more design effort and code. Our code software has some features that can support you in this work, and I will explain that in a glass coating design tutorial. Okay, here we could just keep in mind we can almost achieve the optical properties indivisible of pure glass, but we can also play with colors. And the good news is, if we do that, if we apply different top and bottom oxide layers, the U value versus silver thickness is untouched. It's almost exactly the same. So the transparent oxides do not disturb the good low emission that we achieve with our silver layer. So that's the good news. We can play with colors without damaging the thermal properties of the glazing. Well, unfortunately, there is another problem that shows up. Here we see the transmission in the near infrared of uncoated glass in black, and here in red the transmission of the low E glass that I just discussed. And in blue I show you the intensity of sunlight, and you can see that from the near ultraviolet to the near infrared, and here at 2500 nanometers we have a significant amount of sunlight with a lot of details depending on the sun atmosphere and the earth atmosphere. But what I want to point out here now is, in the near infrared, the transmission of the low E glass is still, well, it's not really high, but it's still significantly different from zero. And here we have also a significant amount of energy that enters from the sun into the building, especially if you have a very large facade. If you replace a solid wall by a lot of glass, you will heat up the building, which is nice in cold areas if you heat up the building for free. But in some other areas and in the summer, you can have a problem by a large heat development inside office rooms, which you then have to fight by air conditioning, which also is expensive. So this is not really the best solution that you can imagine. And this is asking for further improvement. In fact, it can be shown that there can be improvement by reducing the transmission here in the mid-infrared, or near-infrared, sorry. And the easiest way to do that is to add a second silver layer into the coating. This is then so-called double silver low emission, or some people prefer the term solar control glass, in the sense that you control with the second silver layer how much light you transmit in the near infrared. And you can see here a typical curve of a double silver layer with a very much reduced transmission in the near infrared, and with almost the same transmission as that of the pure glass. So this is using this kind of coating uses two silver layers, and it turns out that you need a very thick 80 nanometer, something like 80 nanometer thick transparent oxide in between, a thick center oxide, which is very expensive to make and very difficult to control in the production. So now you have 5 layers, 5 functional layers: the bottom oxide, first silver layer, center oxide, second silver layer, and top oxide. And the production of those layers has been very difficult for a while. Now most companies can produce that in high quality with homogeneous color, um, since the deposition devices have been adapted to this new challenge. The actual challenge is to optimize this further on by adding a third silver layer. And I can show you here a current product of one of my customers with 3 silver layers, basically now 2 center oxides, 1 top and 1 bottom oxide. So you have 7 functional layers for the optical properties, and this gives a very kind of switch for the transmission. You go from high values to low values in a very narrow spectral range. It's very steep, a very steep increase of the reflectivity due to 3 silver layers with a lot of silver typically. And this is now the state-of-the-art product of some of my customers with very long coaters, because you need a lot of cathodes to produce coatings like this, and a lot of experience in order to make homogeneous color for those 7 layers. Okay, a typical coater looks like this. You have the glass entering a large volume of vacuum, where you have a lot of pumps, deposition devices in between, usually cathodes, sputtering cathodes, and if you want to produce oxide, you pump in or you have some gas inlets, so you do this by reactive sputtering. Methods just need metallic targets without any oxygen or nitrogen, and so this scenery here is a principal sketch of a coater that produces a double silver coating. The substrates are usually 3 meters 20 by 6 meters. That's a common size of glass panes. And the glass moves through the coater and comes out completely coated on the other side of the vacuum here to the right. I will now address some common problems of large area coaters. The first problem is the reactive sputtering. Here I show the deposition rate for a sputtered oxide versus the oxygen flow. If you have a gas flow and you sputter a metallic target, then the oxygen or nitrogen, in this case oxygen, mixes with the metal atoms and they produce an oxide on the glass. There's a metallic mode where you produce substoichiometric oxide. Let's say it will not be a titanium O2, but it will be maybe titanium O1.8 or 1.6. If you have very large oxygen flow, you can be pretty sure to produce titanium dioxide. That's what you want. But the deposition rates in the oxidic mode here and the safe mode are very low. So this is a stable production, but with low deposition rates. And there's a transition area here where you have not very reproducible deposition rates, but this is challenging to produce somewhere here in this transition range to combine high deposition rates with a deposition of an almost transparent oxide, very close to the stoichiometric case. So this challenge to produce somewhere here in this unstable area requires that you control what you produce. You can never be really sure what the current deposition rate is. So your large area deposition should be accompanied by a production control in real time. Otherwise, you produce for a long time junk, and which would be very cost ineffective. So what you need is a real-time production control, and you can only do that usually by optical inspection. I will address this point in the next minutes. A second problem is that usually the titanium dioxide that is preferred by most people for the bottom oxide growth, if you do the deposition by sputtering with high deposition rates, it grows with a certain surface roughness. You can imagine that there are some columns that grow, and the centers of the column grow a little bit faster than the edges. So you end up with a certain roughness here. If you deposit the silver layer on top of the bottom oxide, the silver will basically fill the valleys here of the titanium dioxide, and it will then end up with its own roughness, which is usually much smaller than the titanium dioxide roughness. And then if you deposit the top oxide, you do a lot of rough bombardment of the silver layer with high energy argon ions in the plasma of the deposition, and also with the atoms that you sputter to produce the top oxide. So the sputtering with high deposition rates usually is a very destructive process concerning the nicely smooth silver surface. So you generate some surface roughness again, and also you generate some roughness on top here. So this means that the electrons in the silver layer move in a let's say a 10 nanometer silver layer, which has a rough bottom interface and a rough top interface. And what happens then is that the electrons lose their momentum when they hit a rough surface. Basically, they are accelerated by the electric fields of the mid-infrared radiation. They hit the rough surface, they lose their direction, and they have to be accelerated new. And this generates a damping of the electrons, or basically a low mobility. And this has an effect on the U value. So if you have a certain damping constant of the electron motion, the damping constant is a parameter of the simple Drude model that you can use for the electrons in silver. And these are typical values for sputtered silver layers. The damping constant can be somewhere between 200 and 1000, 1/centimeters, and the damping has a strong influence on the U value. I had shown you that you could have U values of up to 1.1, of down to 1.1, sorry. If you have a very smooth silver layer, a perfect high quality silver, you can still reach something like 1.1 with a 10 nanometer layer. But if the surfaces are rough, the damping is high, the U value goes up to 1.35 or even 1.4, which is a big difference. And in some countries, you could never sell low E glass, which has a U value of 1.4. You need to be in this range, 1.1 to 1.2. So you have to avoid the roughness of the silver layer interfaces. How can you do that? You can do it by two things. Actually, you need two additional layers. It turned out that you can deposit a smooth bottom oxide on top of the titanium dioxide. Usually you can use zinc oxide here, and that has the property that it fills the valleys with zinc oxide, and it ends up with a very smooth top interface, which you then can use to deposit the silver layer as a very nice homogeneous layer without any roughness, or without much smaller roughness as before. Then, before you deposit the top oxide, it turned out to be useful to protect the silver by another metallic layer, which is usually made of titanium or nickel chromium, and that layer is very thin, and it has the function that it protects the silver from the bombardment of sputtering atoms or ions here, and it also protects the silver from oxygen incorporation. Usually these thin metallic layers are very strong absorbers, so you have to make sure that they oxidize either during the coating process or immediately afterwards during the first minutes or hours of the coating lifetime. They should pick up oxygen, be ideally completely oxidized and get transparent, so they have done their job to protect the silver. Then they oxidize, and they probably or they ideally get part of the top oxide system here as transparent oxides. So now we have 5 layers, which makes the life of operators in the plant a little bit more difficult. And you can imagine if you deposit a double silver stack or a triple silver stack, where you always need a silver protection layer and maybe also some protection here against surface roughness at the bottom side, you end up in depositing many layers, like in between 10 to 15 in a typical triple silver coating. Let's come back to the production sketch, to the production line here for the double silver. What you typically have is an optical inspection network. That means you have some sensors here that measure optical properties of the coating, of the coated glass. Usually inline here you have transmission probe heads. They send their data, their measurements, to a network, and which is then used to pick up those spectra and to analyze the production that you have at the moment. At the end here, when the glass comes out, you have more space and you can do mechanical motion. So usually here at the end you have a traverse system doing a complete scan of the glass from one end to the other. And then you try to combine all these data to provide a complete picture of what the current state of the production is to the operators. Here is a sketch of sensors. Usually you have transmission sensors that you can distribute at stationary points inside the vacuum coater, with basically some light guides outside or some electrical cables going to the outside only. Here at the end you have the traverse system, usually using 3 spectrometers that measure the transmission and the reflection from both sides. And here you can do measurements across the glass. Typically you measure at something like 10 to 30 positions on the glass. Maybe on the 3 meter wide glass you measure every 10 centimeters. That means you have 30 or 32 points. And if you have a cycle time of, let's say, 60 seconds or 40 seconds in a modern coater, you have about 1 second measurement time for each position if you scan the glass. And that can be achieved with modern spectrometers in very high quality, so you can measure reflectance and transmittance spectra in high quality across the glass here at the end, and then do the analysis of these measured data in real time to provide thickness profiles to the operators so that they know what they should do in order to keep the production as stable as possible. Okay, this was the introduction to glass coatings. I will discuss details and address some additional problems in future tutorials. This was what I would like to show you today, and I thank you for your attention, and you should watch out for more tutorials about glass coating design and production control. Thanks a lot.